Now that we understand what is a sample space, event is much easier. Event is just a subset of the sample space. So very simply, here, if we carve out 1 and 2, that's an event. Okay, it's a subset. Mathematically, it's a subset. So it is a sample space. But sometimes that subset also gives rise to very meaningful human meaning. For example, 1 and 2, this subset is a subset of the sample space 1 to 6. But because these are all low values, we might say the low numbers, right? The small numbers of the dice. So if you want to say something like, what's the chance of small numbers appearing, where small means 1 or 2, then 1 or 2, that set of numbers, 1, 2, a subset of the sample space, is an event. So again, it is just a name, right? So the event it is not a wedding event or graduation event or what. It is a set, right? And this set must be a proper subset of the sample space. Okay, right. So mathematically it's beautiful, it's nicely defined. You just need to associate this commonly used English name. That's where the confusion comes, right? We all understand sample, we all understand space and events, but used in the context of solving statistical probability problems, that's when the confusion soaks into the mind of students or beginning learners. And then you get really confused, right? Because you try to understand event as the way you understand event in English. That's may help, may not help. It is very confusing. Sometimes it is very nice and fitting. Sometimes it is like completely out of the correct understanding. So if it is a subset of sample space, then it's very simple. Now, what's the event? Remember, it's a set. What's the event of odd values? That the dice, when we throw it, appears with an odd label on top. That's simply 1, 3, and 5, right? Yeah, okay. So then we ask, what's the probability of an odd value occurring when we throw a dice? Well, remember counting. So we count the odd value event. How many numbers are there? 1, 2, 3, right? We don't really care about the label. You can call it ONETHRE, you know, spell it out in English, write it out in Chinese, and just script it out in Arabic or other languages. Doesn't matter. Right, so we just count the number of items in that set, and that is 3. And then we count the number of items in sample space. Remember, that was our universal set, right? So this is our universal set, 1 to 6. So there are 6 items. Okay, now here comes the interesting thing. Note that this is another concept of probability. Okay, why is this another concept? Now remember at the start, we talked about there are 3 definitions, and we will mostly be concentrated on data frequency driven kind of definition for probability. Because it's commonly used, it's easily understood, you can count it, you can basically see it, and it's quite easy to understand. So why is this another concept of probability? Now notice that when I drew this histogram, I focus on sharing with you what is the meaning of sample space. So from an abstract definition of a set and name sample space, I put it down as the x-axis. And I did not, I totally did not talk about the y-axis. That is, for histogram, it will be the frequency, right? In other words, when we define sample space, and therefore we define event, because it's a subset of the sample space, we totally didn't have to have any prior measurements. We totally did not need any past events, did not have to know about the high frequency or low frequency of certain events happening. For example, if our dice is chipped a little bit and it tends to show a lot of 6s, and therefore less likely to show any other number. So if one knows that fact, I would always bet on 6, and I would tend to always win, right? However, right off the initial point of solving this problem, we totally did not ask for it, nor given prior data about the measurement of this particular dice, and so we have no idea, right? So we go by counting. What's the chance that 6 occurs? Well, it is that event of 6 occurs is 1, because there's only one label in there. And what about the count of all unique items in the sample space? 6. So it's 1 out of 6. And that will lead us to the sense that it is a fair dice. But is it? We have no measurement at all of this particular dice. And we still proceed with it, right? Because this is our prior probability, our initial assessment, when we didn't know anything about the trickiness or the special setup, of this particular tricky dice, bias dice. We didn't know. We have no idea. We didn't do any measurement, throwing, and recording, right? So we have no frequency information of this particular dice. But yet, we can still write down what's the probability of the number 6 occurring, and that's 1 over 6. So as we learn more about the dice by throwing the dice more and recording down, so 1, 2, 6, 6, 6, 5, 6, 6 occurs a lot, then we start to get a feeling that, wait, 6 seems to appear a lot, right? Let's revise our probability. You get that? So that is sounding more and more like, yes, the second definition of probability that we started off talking. So if you rewind back the video, you will get to see that short discussion, right? So I just went past that very quickly because our main focus is on using data frequency first to define the probabilities of the measurements that we want to talk about. Yeah. So here, this is another concept of probability, just for you to take note of. We still solve the problem the usual way, and exercises, homework, exam questions will come to you with this kind of description, right? So you totally didn't really have to be completely aware of whether am I using the data frequency or am I using the outcome. Because if the question throws to you this way, let's just talk about dice, right? So a dice is a six-sided dice is thrown once. What's the probability of even numbers occurring? That's it. So there's no prior information, no data frequency information, no measurements, no historical records at all, right? We're just given sample space, the possibilities. We were not given any probabilities. And then we are given this event, even number. So even number will comprise 2, 4, and 6. And so for lack of further information, our best guess of the probability of even number showing when we throw this particular dice has to be count of 2, 4, 6. So 3 divided by 6. So again, 0.5. That will be how we solved it for lack of further information. So see, we can still do problems without trying to be very clear about the definition. But some of you might be very curious about, wait, we didn't have frequency. I thought you started with talking about frequency, right? And we now count the sample space. We are now walking along the x-axis. We are counting these items. We're not counting the y-axis, which should be the right way to do frequency-based probabilities, right? You are absolutely correct, and I want to just for those of you who pointed that out, of course you are just pointing at the screen and I'm not aware, right? But yeah, you are right. That is another idea, right, of probability.